Okay, so the next presentation will be from Thomas Rolinger. Thomas is a PhD student in Alan Sussman's group at the University of Maryland, specializing in irregular applications and performance evaluation. But I believe Thomas has been following the development of the CHIUW project quite closely for some time. So Thomas, please take it away.
Okay, so I'm going to talk about ways to optimize irregular memory accesses in CHIUW, specifically doing so through the compiler and having this done automatically, so not requiring the user to actually modify their code to take advantage of these optimizations. So before going into the details of the optimization, I want to talk a little bit about the motivation. So why do we actually care so much about these irregular memory accesses? So on the slide here is a example of a sparse matrix vector multiply written in CHIUW. And a couple key things to note, this is fully distributed. So rows here is a distributed array of records. Each record represents a sparse row. And the access pattern that we care about the most is here. This is a irregular access to X, which represents the input vector to the SPMV. It's also distributed. And we access it through another array, the column index. Now, the key thing from here is that this is really high-level expressive code and takes advantage of CHIUW and overall the PGAS model's ability to write fairly complicated parallel, both shared and distributed memory parallel code. However, the problem is if you run this code, you may not get good performance. So the results here on the right are from a conjugate gradient benchmark, which is going to do a bunch of these SPMVs in a row. And what we see is as you increase the number of locales, instead of getting speedups, you're actually getting slowdowns. So the key takeaway is that while you have high productivity, it doesn't always lead to high performance for these irregular kernels. So the question we ask is, how can we do better? What can we do to get more performance out of these codes in CHIUW? Now, if you're willing to sacrifice some productivity, you could do just a simple transformation, take your 8 lines of code and turn it into something more like 40 lines. And that's being a bit generous. There's actually a lot more code that's kind of hidden here. But the point being is you can manually optimize these codes to get better performance. And we see that here, looking at the green line on the chart. Not only do we get better raw runtime than the original code, but we're actually seeing positive scalability. We're not getting slow. So if you want to take your productivity and lower it, you can get better performance, but to us, that kind of defeats the purpose of what CHIUW's program model provides, as well as the PGAS model in general. So what we're going to talk about here is how we can achieve both. We're going to start with that high productivity 8 lines of code and show how we can automatically get the performance that we just saw without having to actually change the code ourselves. So here's the outline. I'm going to talk about the optimization itself. So what are we actually doing? And then most of the time will be spent talking about how we implement this within the compiler as an optimization. So this has to do with how we do code transformations and static analysis. And then to show that the optimization is actually providing a benefit, I'll look at 2 different irregular applications and see what kind of performance we get. So first, with the optimization, since we're applying it through a compiler optimization and it's done automatically, we need to think about how do we actually recognize what an irregular memory access looks like. So what we're going to say is we're looking for accesses of the form A at B at I, and they're in for all loops. So we focus on for all loops since that's where a majority of all our time is spent. In this case, A is going to be a distributed array, and the values in B are not known until runtime. And this is something that is common in these irregular applications. B is often some sort of data-dependent value. So it could be the non-zero indices in your sparse matrix or the neighbor IDs in your graph. So this complicates a lot of static optimizations because we don't know what the access pattern is until we run the program. So what we're going to do as far as optimization is selective data replication. The idea is to look at the access pattern to the array A and replicate anything that's accessed remotely so that we can use it locally when we run the loop. We do this through a runtime optimization technique called the inspector executor. This has been around for quite a number of years. The idea is the inspector is some sort of runtime analysis that happens before you execute your loop. In our case, it's going to tell us the remote access pattern to A. The executor is then a copy of the original for all loop that's been optimized so that any remote accesses to A will now be redirected to these replicated copies. And while this is a runtime optimization, it's the code to do the inspector executor is generated by the compiler. So it's a static optimization that enacts a runtime-based optimization. And there's 2 requirements worth mentioning about this optimization. Because of the inspector executor technique, we require that the for all loop that we're optimizing is going to be nested in some sort of outer loop. So it needs to execute multiple times with the same access pattern. The inspector has some amount of overhead, so we need to amortize that over multiple executions of the optimized loop or the executor. Another thing is that we require that the access A at B at I is going to be read-only. Since we're doing replication, and if you start writing to replicate data, it can be quite messy if you don't handle it correctly. So for now, we're just focusing on read-only access patterns. It's worth noting that we did manually implement this optimization in our prior work at last year's workshop, but the optimization itself, as well as our approach to how we do this within the compiler, is largely influenced by these other prior works on the slide. So now getting into how we do this within the compiler. I'm first going to talk about the code transformations. So this says, how can we take the code on the left and transform it into something that's functionally equivalent to what we see on the right? And I say functionally equivalent because we're not actually generating a new chapel source code. We're always operating on the intermediate representation of the code within the compiler, but it's helpful to think about what the code actually looks like or would look like. So if we look into this, the first thing we can talk about is the inspector, which is shown in the red box. So again, this is performing memory access analysis before we actually execute the loop. Two key points to note. For one, we need to think about when the inspector should run. The inspector has a cost. If we have to run it too much, then we're probably not going to get a performance gain. So we want to make sure we only run it when we need to. So there's two scenarios. First, the first time we execute the loop, we need to run it because we haven't done the analysis yet. So that's pretty obvious. And then we only want to run it if something has changed the A at B at I access pattern since the last time we've encountered the loop. So for instance, if your values in B have changed, then you have a new access pattern and we need to redo the analysis. So it's the compiler's job in the static analysis, which I'll talk about later, to determine when these access patterns change and essentially flipping a flag. And that's what this do inspector call is going to be checking, these flags associated with the arrays. Another thing to note, when we actually inspect the access, we don't do the remote communication to A. We simply just look at whether the index B at I is going to be a remote access. So this allows us to keep the inspector lightweight, which again is important for getting a performance boost. Moving on, the other piece of code to look at is what we generate for the executor. So again, this is going to be a copy of the original loop that's modified to redirect the remote accesses to the local copies that we created. But before we actually do that, we need to actually do the replication. And that's where this executor preamble comes in. Because we replicate data, we need to make sure that what we have stored locally is in sync with what the original array has. The last time we ran this code, the values in A could have been changed. So we need to make sure we have the most up-to-date values. So this preamble really is just a loop that does some remote reads to A. And that seems counterintuitive because the whole point of this optimization is to reduce remote communication. But the key thing is, regardless of how many times a value is accessed remotely in the loop, we only replicate it once. So we do one remote read to get it, and then we can amortize that cost over multiple local accesses. And again, this execute access call is going to do a similar check that the inspector does to determine whether it's remote, and then it's going to return the local copy if it was a remote access. Otherwise, it'll just return the original local value that wasn't replicated. One last thing to mention here, this isn't specific to the replication itself, but more about how we think about compiler optimizations of this type in Chapel. So we may find out much later on in the compilation process that the optimization can't be applied for some reason. Now this comes up because we do the majority of these code transformations in an early stage of Chapel's compilation because it's much easier to reason about the internal representation before it gets modified. So that means we have all these code transformations done before we even know, for instance, whether A and B are arrays. If they're not arrays, then this optimization doesn't make any sense. So what we do is we create this if then else structure. If we should do the optimization, then do everything that I just described. Otherwise, fall back to the original loop. So do optimization as a flag that the compiler inserts. If we find that the optimization is invalid later on, we will set this to false. And then later on during dead code elimination, that entire if statement will be removed and we'll just fall back to the original code. Moving on to static analysis. So everything I just described for code transformations is only really relevant if the optimization can and should be applied. So we consider this in two ways. When we say the optimization can be applied, it's more of a question of correctness. We want to make sure that whatever we generate as an optimized program is going to give us the same results as what the original program did. If your optimization gives you the wrong answers, then it's not a useful optimization. So the way that we could introduce incorrect program results is if we don't run the inspector when we should, which would mean that we don't have the most up-to-date values because we haven't looked at the access pattern. So to determine when we need to run the inspector, again, we need to know whether this A at B dot access pattern changes. So the stack analysis we do here is fairly involved, but it goes more along the lines of tracking how A and B change within the program. The other thing to consider is whether we should apply the optimization. So this is a question about performance. You shouldn't apply optimization if you're going to get bad performance. That's also not a useful optimization. So what we try to do is ensure that performance gains are going to be likely. And we do this by making sure that the for all loop is nested in some outer loop. So again, we need to make sure that we can execute the optimized code more than once to amortize the cost of the inspector. And this is coupled with ensuring that we're not going to have a situation where the inspector would have to run every single time we execute the for all loop. If we have to do that, then it's a complete lost cause and we'll not see performance gain. So put those two together, and that's how we can at least provide a best efforts check that performance gains are likely. Now, it's worth noting that I skipped over quite a bit of details about the stack analysis and the code transformations. I just don't have the time in this talk to go into them. But if you're interested in more of that, feel free to reach out. But the key thing to take away from here is that these are all performed automatically. So the user is not adding anything to their code. They're not doing pragmas or code annotations or any kind of hints. They simply are just turning on a compiler flag and everything else happens automatically. So the last thing I'll talk about, performance. Again, if the optimization doesn't give us a performance improvement, it's not that interesting. So I looked at two different irregular applications, a conjugate gradient benchmark and PageRank, which is a graph analytic. And I evaluated this on two different systems, your traditional Infiniband system with 32 nodes and a Cray system, which has the Aries interconnect. And this provides an interesting comparison point because when compared to Infiniband, Aries has a much lower latency for these small fine-grained messages. So it gives us a good stress test for the optimization to see if it can still provide a benefit. So for the results I'll show next, they're measured runtime speedups achieved by the optimization when we compare that to the original code on each system. And this also includes any of the overhead incurred by the inspector. So first we have conjugate gradient. This is part of the NAS parallel benchmark suite. So it's going to operate on different problem sizes, which correspond to different sizes of the synthetic sparse matrices that it generates. And you can see those details in the table on the top left. On the top right, we have the table of the runtime speedups. So higher numbers in here are better. It's worth noting that a dash in this table means we didn't have enough memory to run the baseline. So as you can see, problem size F is quite large, so we couldn't do that unless we had 32 nodes on the Cray or 16 nodes on the Infiniband system. And the NA represents in the Infiniband column that we didn't have enough nodes. So it's a 32 node cluster rather than 64. And I also pulled out the speedups in a chart form for problem size E, which is in the bottom left. So the key takeaway here is on the Infiniband system, we see very large speedups up to about 364x. On the Cray, we're seeing about a 37x improvement at best. So the big discrepancy between the two systems, again, goes back to the interconnect. The Aries interconnect has a lower latency, so there's not as much for the optimization to do here. Nevertheless, these are still fairly substantial speedups, and we see these for two reasons. One, we have a lot of iterations within this benchmark, which allows us to amortize the cost of the inspector. And the other reason is that these matrices have a lot of data reuse. So again, that goes back to the fact that we only replicate the value once. So the more times we need to use it, the more time or the more benefit we're going to get through the replication. Next, we have PageRank. So this is a graph analytic. It's iterative. It does a SPMV-like operation. But as you can see in the table on the top left, we run for significantly fewer iterations when compared to conjugate gradient. So we're looking at 30 or 40 versus the thousands that we were seeing on the previous slide. And the table below that, again, shows the runtime speedups. And I pulled out one of the data sets in a chart form. So first, we see a similar trend that we saw for conjugate gradients, in that the Infiniband system sees a larger benefit from the optimization, and that's for the same reason. But the speedups are generally much slower. So we're talking about a 12x at most versus a 360x on the conjugate gradient benchmark. And the reason for that is because, for one, we have fewer iterations here. So the inspector overhead is more dominant. And these graphs happen to have a lot less data reuse. So replication doesn't do as much there. For the Cray system, we don't actually see a positive performance gain until 32 and 64 locales. This is something we come across often with irregular applications. You have this sparse graph, it's partitioned across the system. And as you increase the locales, you're changing the way it's partitioned. Load balancing is changing, the communication patterns are changing. And so it just happens that when we hit 32 and 64 locales, we're starting to get more data reuse, and that leads to the optimization kicking in for the Cray system. So wrapping up, overall, the optimization is producing promising results. Not only are we seeing good speedups, but the actual raw runtimes are quite improved. We're talking about hours and days down to minutes. But there are limitations for this type of optimization, as well as replication itself. So because we're doing the inspector executor framework, we have to have this for-all loop executing in some sort of outer loop. This is not indicative of every type of irregular application, though it does cover more than a few. In regards to replication itself, we do have to deal with the fact that we're adding a lot of memory usage overhead. And because we're doing replication, it's much easier to think about doing things in a read-only way. So that limits us from applications that need to write to the A at B at I access. Now, as I alluded to, there are a lot of things I didn't cover in this talk. Specifically, we have a lot of different analysis we do to detect the modifications to the arrays. We look at different alias analysis, as well as analysis across function calls. So if you're interested in that type of thing, feel free to reach out. I can give you more details. But the final slide here, to address the issues I mentioned before, we want to add more optimizations to this framework. So I started looking at inserting prefetch calls into Chapel's remote cache, and as well as more generalized aggregation, specifically from remote writes. So this could help address the issue of the read-only limitation we have. And by more generalized, I mean doing operations beyond just assignment, which is what copy aggregation does for us today. The end goal here would be a single framework that can apply multiple optimizations automatically, where the compiler would decide which ones make the most sense in a given scenario. And finally, I want to acknowledge the Chapel team. They've always been really helpful and responsive to questions, as well as helping me get access to the Cray. And specific shout outs to the names here. Getting started with the compiler was not an easy thing, and these folks helped a lot, as well as just overall discussions with the optimization. And with that, I'd be happy to answer any questions.
Thank you, Thomas. Yeah, please, anyone with questions, raise your hand or unmute. Michael Merrill asked, but I think maybe you had that question answered already in the future work. Is that what you're saying, Michael? How would this compare to aggregators? You happy with that it being part of future work?
Yeah, I'm okay with that.
Yeah, I would say aggregators are similar to what we do. The way I describe what this is, it's like a giant prefetch before the loop to get everything you need. Aggregators do kind of that similar, but it's more of a buffered approach. So there's kind of pros and cons there. But I think aggregators in the general framework of trying to optimize these irregular memory accesses are going to be really important because they're a little bit more general.
And Tom Westerhood?
I was wondering about the memory usage. You mentioned that it could be a lot, but are there techniques to reduce that or tune it perhaps?
Yeah, so I mean, one thing I thought of is instead of replicating every remote access, you could try to prioritize that. So replicate the remote values that are accessed the most. That's certainly possible, but it does complicate some of the internal workings of how we do the replication. So it may save memory, but it may lead to less performance increases. So it's something I haven't looked at in depth, but it's certainly something that could come up if memory usage becomes an issue.
That makes sense.
Okay, thanks, Thomas, and thanks also to Alan for this work.